This is a Math 2 summary video for the lesson titled Distributing the Area. The purpose of this lesson is for students to multiply linear expressions and factor quadratic expressions. This task reviews the work students completed when they studied quadratic expressions in Math 1. In this lesson, students will use the box method to multiply binomial factors and then follow similar patterns of reasoning to write a quadratic expression in factored form when the expression is given in standard form. Before we begin looking at how this lesson progresses, let's review some key vocabulary. Polynomials are expressions that use addition, subtraction, multiplication, and division to combine constants and variables. In a polynomial, variables cannot be divided and they cannot be located in the denominator of a fraction. Examples of polynomials include constants, like the number 2, and expressions like 3x, 2x plus 4, and x squared plus 6x minus 10. The word factor is used as a noun and as a verb. When factor is used as a noun, a factor is defined as being a polynomial that can be multiplied to another factor to find a product. When factor or factoring is used as a verb, you are being asked to find factors, the noun. It's like if you were going to go fishing. When you fish, you are looking for fish. When you factor, you are looking for factors. In this lesson, you will be given quadratic expressions that are written in standard form, and you will be asked to write them in factored form. You will also be given expressions in factored form and asked to write them in standard form. A quadratic function is written in standard form if it is written as ax squared plus bx plus c. A cannot equal 0 for it to be a quadratic, but for an expression to be in standard form, the terms need to be listed so that the degree of each term is listed in descending order. Recall that the degree of a term is the sum of the exponents. A quadratic expression is in factored form if it is listed as the product of linear factors. Make sure that you keep in mind that not all quadratic expressions can be factored. This lesson begins with looking at how an area model can be used to multiply integers. Keep in mind throughout this lesson that the area of a rectangle is found by multiplying length times width. In this example, 11 is being multiplied by 7, but 11 is broken up into 8 plus 3 and 7 is broken up into 5 plus 2. With the box method, we list the factors being multiplied on two adjacent sides of the rectangle to represent the length and the width of the rectangle. Then we multiply each piece of the length and width together. We write the products on the inside of the rectangle. So, 8 times 5 is 40, 3 times 5 is 15, 8 times 2 is 16, and 3 times 2 is 6. These numbers on the inside of the rectangle represent the area of the smaller pieces of the larger rectangle. To get the total area of the large rectangle, we now just need to add up all of the areas of the four smaller rectangles. Once we add all of our areas of the four smaller rectangles together, we find that the total area of the larger rectangle is 77. The process for multiplying polynomials is very similar. Start by placing the factors on two adjacent sides of the rectangle to represent the length and width of the rectangle. Then multiply each piece of the length and width together to find expressions for the areas of the four smaller rectangles. X times x is x squared. 3 times x is 3x. X times 7 is 7x. And 3 times 7 is 21. The next step is to add these four smaller areas together to get the expression x squared plus 3x plus 7x plus 21. And then finally, to get the expression in standard form, we need to combine like terms. 3x plus 7 is 10x, so the total area written in standard form is x squared plus 10x plus 21. The lesson continues with this example, where you're given an expanded quadratic equation and asked to write the expression in factored form. We need to take our steps from multiplying and reverse them. This means that we need to start by placing each term inside the box. Now we need to find the greatest common factor of each row and column to find our factors. Let's start with x squared. X times x gives us x squared. Then I'll look at 5x and determine that 5 times x will give me 5x, so I need a 5 on the top right of my box. Next, I look at the 3x and determined that 3 times x will give me 3x, so I need a 3 on the bottom left of my box. Then finally, I look at the 15 to make sure that the 3 and the 5 that I found will multiply to get 15. Now that I have found the length and width of my rectangular box, I can write the area of this rectangle in factored form. The final example that we'll look at reviews what to do when you're asked to factor a quadratic trinomial when the coefficient of x is 1. We need to start by finding two numbers that multiply to get 24 and add to get 14. Those numbers are 12 and 2. If I was having a hard time finding my two numbers, I would have made a list of all of the factors of 24 so that I could check their sums. Now that I have found 12 and 2, I use them to split up the 14x. This gives me the 4 small areas of my box. Now, this example is just like the previous example. Once I have my box filled out, I just need to find the greatest common factor of each row and column. Then I take the length and width of my rectangular box and use them to write the quadratic expression in factored form. To summarize, in this lesson we found that multiplying and factoring polynomial expressions is a similar process to multiplying and factoring integers. We also related this process to finding different ways to represent the area of a rectangle. The area of a rectangle can be expressed as the product of the length and width of the rectangle. The area also can be represented as the sum of the smaller areas that make up the area of the larger rectangle. We also found that when you're factoring quadratic expressions, when a is equal to 1, you need to find two numbers that multiply to get c and add to get b. These numbers are used when you write the expression in factored form. In the next lesson, we will look closer at factoring quadratic expressions when a is not equal to 1. Thank you for watching.